Welcome to the third BSBF Webinar mini-series. I look into the future of big science organizations. I am Manuel Moreno, a Spanish Industrial Liaison Officer. I'm working for CDTI, the Spanish Innovation Agency. First of all, I would like to thank the participants and speakers. At today's event, we are going to focus on the strategy vision, roadmaps, and development programs for high-energy accelerators and synchrotrons research organizations. In this webinar, we take a step ahead and identify the technologies that will drive these organizations in the future projects, analyzing their strategies and their research and development programs, and how the industry can be involved. The agenda of the webinar is broken down into the presentations from the 6 speakers from the Esrf, ESS, Esrf, FAIR, European XFEL, and ESS Neutrino Superbeam project, who will each have 20 minutes to lay out their future plans. When we finish this part, Anna Hall, Director of Science, Sweden, will moderate the question and answer session. Before we start with the webinar, we would like to share a short video about the BSBF 2022. Sorry, because I can't see the video. Okay. Okay, we hope the video has been of interest with you. Please take a note of the important date. This beside the registration in BSBF is currently open through the web page with early bird registration closing on 30 April 2022. Okay. Now we can start with the presentation. As I say, please submit your question using the question and answer module, and we will address a selection during the roundtable. The first speaker will be José Miguel Jiménez, the head of Accelerator Technology Department at Esrf. We are grateful to you for taking part in this webinar. Please, José Miguel, can start your presentation. José Miguel. Okay.
Yes, do you hear me?
Yes.
Yes, okay, good. And you see the presentation or not?
No, not yet.
Not yet. So, and then now?
Now it's okay. Yes.
We are in full screen mode. Okay.
Yes.
So good morning, everybody. Sorry for this small technical problem. I hope that we will not get more because we have the internet connection very unstable this morning. So the first thing is to thank the organization committee for this very nice opportunity. And in fact, starting the day with some pictures of Granada, the city where I was born, is for me a very big pleasure. So I'm going to try to introduce the activities at CERN in the next 20 minutes, which is already quite a challenge. You will see that I will not be covering all the slides that I put in the Indico page. So please look at them. You have plenty of much more detail than what I'm going to present. So first of all, just to remind the mission of CERN, and as our Director General said, CERN smart objectives, specific, measurable, achievable, realistic, and time-bounded, are to pave the way for a vigorous R&D development program and future plans for accelerators. So clearly, in the next 5 years, it will be crucial for the full exploitation of the LHC, and as well to pave the way main objectives: deliver world-class scientific result and knowledge, increase the return to a members and associate member state, and finally, a third one, which is coming more and more powerful in all aspects, which is to strengthen CERN impact on society. So I will be covering the 4 pillars of CERN accelerator chain: the response to the European strategy, the high luminosity and LHC full operation, technologies and expertise, including some aspect of infrastructure, and finally, research and development and the opportunities for you and for us. So clearly on the first point, we are committed to deliver a first world-class scientific result and knowledge with a successful run-free and operation of the high luminosity LHC and upgrade of the large Atlas and CMS detector, with also an increased development of a scientific diversity program, neutrino platform, and theory to open new avenue of exploration. And this is also in line with the preparation and actively preparation of our future by reinforcing accelerator R&D feasibility study for future circular collider, and also some initiative in the scientific diversity program and computing R&D and accelerator R&D. So the first project, the first study is the future circular collider with an electron-positron Higgs factory, which is the highest priority for us next collider. And then on the second phase to go for a proton-proton collider. The idea is to build a 100-kilometer machine, and this is what I'm going to show in the coming images. You see here the two options. So the one with you see the first one with the electron-positron collider, and the second option with a hadron-hadron collider with a machine of about 100 kilometers, which will be based in the zone of Geneva. So this is the first study which is ongoing at CERN. And just to give some ideas where are the challenges, you see here the profile of a tunnel on the ground with all the difficulties of not only the neighboring, but as well all the challenges from the technical point of view, because all the cooling and ventilation distributions, electrical distribution, powering, all these aspects are of major importance considering the size and the depth of all these machines. So in terms of R&D, we are mainly looking at cavity studies, superconducting RF and substrate technologies in order to as options for higher gradients and high quality factors for the cavities, cryomodule development, power couplers, and in order to optimize and the transfer of energy and the acceleration gradient, and finally the power sources in order to decrease the electrical footprint of the FCC-EE option. In terms of milestone, in addition to all the industrial studies and feasibility studies of the underground and the surface infrastructure, we are going to prepare a full scalable mock-up of the magnet and vacuum configuration. So you see here the combined dipole geometry, which we are studying with all the aspect of synchrotron radiation, which are happening in this machine, like in all synchrotron radiation facilities. And then we see here some larger dipole and combination quadrupole that we are looking for the for the approval, we hope so, and constructions. So linked to the FCC, we have a second step with a hadron-hadron collider, and because this is going to be staged in time, then we are also looking for new technologies, new developments with looking at the ultimate performance of an urban fitting high-field magnets, HTS high-field magnets, and as well all the development in the conductor in order to be sure that we will be able to reach the objectives of 100 TeV. So this implies working on both the axis of the magnetic field and on the total magnetic length, so the industrialization capacities of the technologies. So clearly we see here going from high luminosity to higher robust magnets in order to be able to produce them in series, or to increase the magnetic field using some HTS insert or HTS magnet, and also pushing the ultimate urban fitting technology. The second study which is on the table is the compact linear collider. So a very clean physics linear collider on electron-positron. So this this project is already at a much more mature stage, and we see that we already did a lot of development on the cavities, on the beam instrumentation, on the couplers, etc. So this is at the moment have been most of these technical solutions have been approved, and are used in the CTF, in the click test facility, and have demonstrated very efficiency. So as the next step, you see here, this should be 3 phases of click. The first one, which is a 380 GV, and then we have the upgrade to 1.5 and 3 GV. And you see here the scale for the next years with the first phase, second phase, and third phase. And obviously, you probably heard that the energy optimization is one of the challenge for these click options. So in terms of operation, second chapter, high luminosity and LEC, which are the priorities for CERN in the coming years. You see that we are already with all the civil engineering completed. So this is
Sorry, Jose Miguel, I can hear. The connection.
And certainly we have developed in the past years some methodology to handle all these long shutdown activities, and also to implement and run all the infrastructures. So you see here some example of cryogenic cooling and ventilation system, which have to make less and less noise, and have to be inserted in some more and more dense sites. So this is new challenges that we have. Similarly, the energy management and distribution is a continuous challenge for all the machine, from the powering up to the distribution and the cable supply, which is quite difficult at the moment. The logistic are aspects which are very important for the installation and later maintenance of all the machines. And clearly the cryogenic operation of a very large liquid helium infrastructure is an asset of CERN, and we need to maintain all the 27 liquefaction plants that we have at CERN, and this is also requires a lot of contracts and technological support from industry. We develop also in the recent years, and this is one of the reasons why VLHC is operating very safely, a unique expertise for the large electronics to detect any anomalies on the superconducting have to replace most of this equipment, and this is something that we have on the pipeline, as well as all the development and upgraded of the thousands of power converters that we have, not only in VLHC but in all the injector chain through the different machines. And this is a consolidation which is ongoing. And finally, also the controls, which are very important in order to adapt the different system, and the capacitors which we are using in order to take less energy from the network and try to optimize our electrical footprint. So we have also development which are ongoing, because we are increasing the energy, we are increasing the brightness. So we have to improve the performances of all the septa, injection and extraction septa along the machine, with a lot of difficulties and challenges that need new development with industry. And also the beam instrumentation need to be adapted to this new configuration of electronics and beams. Finally, because of the huge length of different accelerators, so more than 100 kilometers of beam pipe, we are now developing some expertise for the re-engineering of a normal conducting magnet because we have to continue the process of consolidation of all the machines that we have at CERN. And these are some examples of activities which are
I'm sorry, Jose Miguel, I can hear you. I'm sorry, because we have a problem with the connection of the server. I hope to repair. Jose Miguel, please, you connect your microphone.
Yes, do you hear me?
Yes, now it's okay. Now,
okay.
We have some problems about the connection with the sounds. Okay.
So when did you lost me? I continue?
I continue in the last is about the I don't you put.
Do you see the slides?
No.
You don't see the slides. Okay. That's going to be. Okay, do you see the slides now?
Yes. Yes,
okay. So I will, in the interest of the agenda, I will continue. I'm very sorry for all these technical problems. So I was mentioning that we have a very important infrastructure for cryogenic, for liquid argon neutrino baseline at CERN, and contribution to the future Fermi Lab infrastructures. We have also all the technologies and setup which we need to update and upgrade continuously for the high field magnet, like the manufacturing of the wires. So we are buying the conductor, but we have to manufacture the wires. Some of them can be done at CERN, some of them are done outside. We have all the infrastructure to manufacture with the support of industry the magnets at CERN for the next generation. So you see here the niobium 13 for high luminosity. Also the superconducting devices in collaboration with industry and with European institutions in Europe and in member states. So you see here the superconducting link with 110 kiloamps at 25 Kelvin. And some other cryostating that we are using to test all kinds of configuration in the lab. We are also running the largest beam vacuum system worldwide with more than 120 kilometers with a reliability close to 100%. You see all the details, and for that we have developed very large vacuum infrastructure which are useful for CERN, also for some collaboration and as well for industry. You see here an example where we were contributing with the industry for the validation of the cryostat for the ARIA projects. And if I continue, we also develop chemistry expertise for all kinds of surface treatment and coatings, which are very important for the machine. So in this case, electroplating of copper, silver, and any kind of process of wet processes, and also of plasma processes, for which we are continuing the development of different type of coatings and neck coatings in particular. So I'm not going to cover the vacuum engineering, quite a lot of activities. We are doing the design and we are making the production in industry. And this is at the moment going full speed for the high luminosity installation. And finally, the last topic that I would like to cover is the research and development. So reliability, availability, and for all the beam failure cases studies. So we are collaborating with institutes and industry for the validation of all the consequences of beam losses and at very high power. We are studying at the moment the potential distribution of the power ring for the FCC, which is very important to consider the stability of the electrical network and also the capacities to detect any problem in the electrical network and control the energy extractions from these 100-kilometer lines. Beam physics application more and more computerized and with more and more development. So this is what
José Miguel, we have another problems about the connection and apologize. Okay, we have serious problems about the connection. José Miguel? I think we lost the José Miguel, the connection of José Miguel. And we wait 1 minute. Okay. José Miguel, please connect your microphone. José Miguel?
Yes,
okay.
you lost me again.
Yes.
Okay.
Just,
but this time was not CERN, I don't think, because okay, anyway, I mean, you have all the slides. I'm very sorry for that.
Don't worry, because I record this presentation and
okay.
I give the possibility to listen after, okay?
Okay, so we also develop example of quality step in the for the very high standard of ultra high vacuum for high brightness and high energy beams. So this is something that we will be very happy to share with our institutes or industries and to explain the processes. So this is what is leading to the very high quality of the vacuum in the different machines at CERN. Also developing some modeling. In this case, you see on the right side the modeling of sparking in a structure of click. So we are in capacity to really model the sparking effect and then the propagation of the spark and the on the RF structure, and to see all the effects which are linked to that. So these are studies which are very important for the reliability and availability of the click machine. And also we are at the moment on the process, quite extensive process to replace all the high voltage switches and the low loss cable that we need for interconnecting the power supply.
And apologize because for these technical problems. Okay, this webinar is being recorded, and all the presentation will be able on BSBF web page. And so sorry. José Miguel, another time we lost. Okay. I wait. Definitely, we lost José Miguel. And Okay. I think okay, Jose Miguel. Yes, we have a serious problem with the connection or with Earth. I don't know.
Okay, do you hear me?
Yes, now yes.
So I'm trying again.
Yes.
I'm very sorry for that.
We have 5 minutes to finish.
Yes, but I'm close to the end. So I think we got disconnected at this level of the cavity. So a lot of needs, in particular for the FCC-EE, for the multi-cell manufacturing, not only of bulk niobium, but also different options like coatings on copper, so niobium coatings or niobium fitting coatings on copper. So the activities and also on all the optimizations of the click RF structure. And finally, again, because we are increasing the intensity and the energy and the brightness of a beam in many different machines, we have a vigorous program which has been launched on the sources, the targets, and the beam dumps and collimators, and we are collaborating with a lot of industries and institutions on these aspects. So again, just to conclude, you have all the slides. I think probably the interaction at the end of this webinar will be much more efficient than my presentation because I got cut so many times. So the impact on the society is in many ways, I mean, the scientific knowledge, which is our primary mission. The values, we would like to continue collaboration across the borders and inclusiveness and openness with industry, with all kind of partners of CERN. The scientific training is a priority, so the contribution to tomorrow's workforce, and we have exchange with industries already in place, and we would like to continue developing because we can also help the industry and learn from the industry on many different execution processes. Development of advanced technologies, clearly this is a challenge. We have to change the present technologies if we want to stay within the environmental objectives that we have, and also keeping the challenges of the higher energies and energy frontier. And finally, we have to work on sustainability and environment, as I said, to minimize the laboratory's impact on environment and continue with the energy savings and reuse options of our lab. So that's all for me.
Okay, thank you, Jose Miguel, for laying out all these interesting projects. And well, there are some problems about the connection, but don't have any problem. Okay. Okay, the second speaker is Matt Lidros, the head of accelerator division at ESS. As you know, ESS is currently in the construction phase. Please, Matt, can I start your presentation?
Okay, can you hear me okay?
Yes, it's okay. Yes,
and
thank you.
You can see my presentation in
yes,
full.
The full screen. Yes, okay.
Okay, so I will talk about future R&D at ESS, some focus on the future, but I will start with a quick review of the facility where it is today. It's of course for many years been on the paper and now it is a reality. So I will be very fast through the overview. So, but the presentation is available afterwards, and you can look at the slides. And then I will spend 4 slides on talking about the future R&D options at ESS, which I guess is the main focus. So this is a picture from this summer or late autumn at ESS, and you know that we are building a European research center for the world, and you have Max Lab, which is a national facility in the background, the first high brightness light source, and then of course ESS and Science Village, which is supporting infrastructure in between. First thing which should be stated and made very clear is that ESS is built by European collaboration. When I came 2009 to ESS, I was the only person with any accelerator background. And of course, having to launch a project starting 2013, to find the partners in Europe who were actually able to do this work was crucial and essential to even be able to do this. And I give you an example just here of all the partners, 23, that have contributed to make the accelerator come true. And these are spread from all over Europe, of course, where Spain is an important partner in this project. So what is the status today? You see aerial view of the ESS facility, and we are now completing all the buildings. So CF, the conventional facilities, will be handed over at Christmas. We are building a phased approach to ESS, so 2 megawatt and 15 instruments will be ready for start of user operation. For the accelerator, presently we have a date for ready for beam on target in August 2024, and we are now in discussions with Council. There's Council meeting this week after a rebaseline review to weigh in the impact of COVID and other accumulated delays. A contingency on this time when the facility should be available for user operation and the additional budget that is needed for it. So I can't comment on that as Council takes place this week. So a few project highlights. The accelerator infrastructure is largely in place. It will be completed this spring. This is all the cabling, process pipe, cable ladders, and everything that you need to actually make the facility work. The normal conducting linac, which is ESS Bilbao in-kind contribution, is installed and ready and operational with 6 klystrons. The process piping, you can see some of it up in the RF cells further on with the power supplies and modulators that actually was developed in Lund by ESS, but in collaboration with ESS Bilbao and built in Spain. You can see the cryo module testing. This is superconducting linac, and we test elliptical cryo modules in Lund, but also in Uppsala, and this is in full swing with serious cryo modules arriving weekly for the moment at ESS. The DTL is built by INFN, and here you can see the DTL workshop at ESS. They are too sensitive to transport, so INFN works here at ESS. This is the DTL1 installed, as it was installed in the tunnel. It's now integrated, and we are operating from 2 control rooms temporarily with a full control room soon being ready for operation. We just took beam from the ion source, recommissioned. Ion source is from INFN, Italy, Catania. We took beam through the RFQ this week, and this is the first pulse of beam through the RFQ, and that we had this week. And we will commission it fully before Christmas, and then continue with DTL conditioning and eventually being through DTL. To enable this, of course, we need control systems, and we have a control system hardware platform, and EPIX as our standard control system. And this is all integrated through the control systems. We have target integration and S integration and CF integration also in the controls. And this is unusual because normally controls can be quite segmented at facilities, but we use the same control system and same infrastructure everywhere at DSS. The control system infrastructure is in large installed and operational. And they also deliver the machine protection system and the personal safety system, where we today has all the parts in operation for the normal conducting linac, of course, and all the permits that we need and license to operate it as we are now operating. Here you see some of the software that is presently in operation that has been developed by ESS, but also by the European partners with different subsystems, and they are now in full operation at the facility. Architecture feature is this Cantilever Roof, also called the sombrero by visitors to ESS. It's now complete and in place. Of course, as buildings are handed over, you can see the target building, the entrance, which will be the main part from the office building, in operation. You can see the target monolith, where all the infrastructure and the target coming from ESS Bilbao will be installed this spring. You can see already the vacuum vessel in place, and you can also see all the supporting infrastructure with all the beam extraction ports, which are presently being welded to the vacuum vessel at ESS. On the lower left, you can see the vacuum vessel being lifted in place that was manufactured in Spain. You can see all the parts of the target system, all the tungsten bricks being installed, and also the hot cells, which are a UK in-kind contribution, where we're going to handle the target and take it apart once we're going to store it. The utilities and all the transport equipment that has been delivered by European industry, and the target system infrastructure for it, including the ventilation, which is of course a major issue for such a facility. In the experimental halls, the Hungarian contribution here on the shielding and the custom-made shielding for each instrument. You can see how this is being put in place, and the first detectors now coming in place at TSS, including 2 of the experimental huts being completed and being made ready for operation. You can see some of the experiments, including some of the neutron guides that are now, because this is a long pulse facility, which means that we have long flight times to separate in energy the neutrons in place, and all the supporting sample preparation labs that are to be used for the scientists to prepare the samples, which are already operational at TSS. Labs and experimental buildings. You can also see the support buildings for ESS and the waste treatment facility, which is now being set up so that we can handle the radioactive waste that we need. So that was a very quick run through, and as I said, you are warmly welcome to consult the slides. They will be updated at Indico with the latest slides that I had this morning from my colleagues. So what are the R&D drivers at ESS for the future? First of all, the full scope of ESS is a 5 megawatt facility with 22 instruments. And as I said in the beginning, presently we are doing 15 instruments, with 8 being ready for start of user operation. And we want to recover the full scope of the 22 instruments in the first operational phase of ESS, and also to recover the full 5 megawatt accelerator. I did mention, but I repeat that the ESS accelerator has all the cryo modules, all the superconducting linac in place for 5 megawatt, but not the RF sources yet to power more than 2 megawatt for the facility. So it's maybe an upgrade of RF sources when we upgrade to the full 5 megawatt. We need new technologies and new software developments to increase the number of user days, gain reliability, increase science reach, and improve the energy efficiency of this facility. And this can all be implemented as we take the next step to upgrade to the full scope of ESS. The third driver for R&D is, of course, the future upgrades of this facility. It has a projected lifetime of at least 40 years. And if it goes beyond that, that is, of course, our innovations that will make it continue to be a world-leading facility for neutron research in Europe. And some of the future upgrades that we are working on and will work on with industry and partners is, of course, new, innovative, and improved instruments. There are many ideas around what can be done and improved in the next generation of instruments, including some of those up to 22. We have experiments for new applications. For example, there is collaboration driving a neutron oscillation experiment in fundamental physics, an MBAR. And this is an exciting experiment which has great potential to answer some of the big questions in particle physics and contribute to the understanding of it together, of course, with LHC and so on. Increased beam power beyond 5 megawatt for a second target station is something that we are thinking about. I'll comment more about what can be done here. And in the long-term future, maybe an accumulator ring to actually also build a second target station for a short pulse target that would further increase and enhance the capability of ESS. Software developments is continuously ongoing. We have an AI group that works on applications for beam tuning, but also for all the analysis software supported by the EDMSC, the computer center in Copenhagen, which is part of ESS, to support users with the way to analyze the data, but also to plan for it and to be able to make the optimum out of their experiments. So to recover the 5 megawatt scope for the accelerator, which is the most immediate need for focus for me, is of course that we As I said, we have 5 megawatt accelerator installed. We will have 5 megawatt installed when we are start user operation. And we then plan for a staged increase of the number of RF sources, and that is klystrons and modulators, which we will order them in European industry. We also have plans with European manufacturer on high efficiency klystrons, which they are working on together with CERN. This gives improved energy efficiency, and we follow that development with interest as a way forward for the ESS facility. For new technologies, on one side you have, as I mentioned before, new innovative and improved detectors and instrument technologies, which would increase the physics reach. We also have the superconducting RF technologies, which are still developing. We see higher gradients every year for superconducting cavities. We had an ambitious goal, which today is proving to be achievable in our test stands as we test our cryo modules. The cryo modules are built in France at CA and CNRS, I should mention, as an in-kind contribution to ESS. And we are planning to build an Esrf facility at ESS to be able to maintain and repair and improve the superconducting part of the LINAC. As there is a strong European Esrf community, we also will be part of that and continue and refine the Esrf technologies for future replacement of additions to the superconducting LINAC to be able to take higher performance of it. The solid state technology for RF amplifiers could replace some of the lower power tubes technology which we are using presently, and that would also result probably in increased reliability of the facility. New beam instrumentation, we have some very innovative beam instrumentation developed partly in many different in-kind partner labs from Italy to in Germany and in France at CA, and this is of course crucial because we need to see the beam to reduce losses and enable a reliable high power operation, and we will continue to evolve that and add instruments as we go on with the facility. AI technologies I mentioned already, for accelerator especially operation and tuning will increase availability and simplify operation. We also have moderators. We have one moderator at ESS that is where we slow the neutrons to make them available at the right energy for the users. And we are now working on a high flux moderator, which there is place enough for that in the facility. And that would also increase the science reach with the further next generation moderators. When it comes to the long-term future upgrades, we will continue, of course, to work on detector and instrument technologies that is always an option and can be gradually upgraded and put in place, as well as totally new instrument concepts in the many slots that are still available. We have over 40 slots available at the present target station for instruments. I mentioned the second target station for short pulses that would increase science reach into a new domain. And if we talk about Esrf cavity technology, we have 5 megawatt capable LINAC, which will be installed, and we have space enough with present technology to go to 7.5 megawatt. But of course, if we use new cavity technology, we could probably go beyond that and deliver to 2 target stations, for example, 5 megawatt of beam. An accumulator ring for short pulses has many challenges and many interesting developments that we could undertake if Council permits us to proceed planning for something like that and do R&D. And here one side is an H- source, but also for acceleration, you will need to strip H- ions. We accelerate H+ ions in the facility as it is today. And H- injection, the laser stripping, is the key word these days, and there is experiments at SNS to take away stripping foils and replace that with lasers, and this is something we will of course be very interesting to apply here at ESS. If we build a storage ring, new magnet and storage ring technologies could enable a very compact accumulator ring with low losses. And fast extraction systems taken from the click developments, fast rise time and fall time, could permit us then to match a train of pulses to the target so that we match actually the proton pulse length to the moderator time constant, which significantly, we talk about factor 30, would increase the neutron flux for the users at the short pulse station. So you see there is plenty of opportunities for R&D and things that we will work on and make sure once we have completed the stage 1 of the ESS and put user operation, where start of user operation is of course now the focus of the whole project to conclude on the schedule that we have promised with the budget that we are asking to complete this. So as you can see, there has been considerable progress on site, and if you come and visit us, and I hope you will do that, you will see that this looks like any major accelerator facility in the world today, an experimental facility. We have met the normal conducting schedule date since the beginning of 2021, and we had a 2-week delay here with RFQ commissioning due to some unforeseen delays, but the first beam was then taken this week through the RFQ, and we are seeing very good results of this RFQ, which was built at CA in France and by French industry. Civil construction, I mentioned, it is to be completed 2021, and when it comes to R&D, for the first phases, of course, of ESS, what we install now, that's largely done, but there is plenty of opportunities over the coming 40 years to develop technologies for an increased science reach. And short term, there are opportunities for scope recovery, the 22 instruments and the 5 megawatt facility with RF sources and modulators, all made by European industry today. And there's no reason that should change and that we should be able to continue that. We also have long-term opportunities, which is actually really only limited by our imagination, what we can do at ESS and improve this facility. Finally, I just want to conclude and say that ESS is built by European collaboration, and it works very closely with European industry, and it demonstrates what I believe most firmly in, that together we are strongest. Thank you.
Thanks, Matt, for illustrating us the research and development drives, new technologies, and the future upgrade at ESS. Okay, next speaker is Jean-Claude Biasi, the head of Technology and Research Development Division at Esrf. Jean-Claude, please go ahead with your presentation.
Yes, I hope you can see my screen.
Yes, full screen. Yes, it's okay.
Screen?
Now.
Okay.
Yes,
so thanks, Manuel. Thanks for the organization and to give me the opportunity to give you this presentation today. In fact, I will cover briefly what is Esrf upgrade program, because we had a huge upgrade program in the past years that will end in 2022. What are our main projects, future plans, and what technology and challenges, and also collaboration opportunities. So first, we had a huge Esrf program which started in 2009, and you can see it was divided in 2 phases, phase 1 and phase 2. And phase 1 was mainly the opportunity to renew many beamlines, 29 beamlines with their end station. The opportunity also to have additional building, Chartreuse and Beldon Hall, as you can see here around the ring, which represent something like 8,000 square meters. And it was also the opportunity at this time to improve a little bit the accelerator system. Concerning the infrastructure, I need to mention also that it was the opportunity to have in 2012 a very high quality slab for experiments, a very stable slab, and this was a huge program work with civil engineering companies who were able to achieve our specifications. in phase 2, in fact, the phase 2 is the renewal of the accelerator. In fact, we replaced all the storage ring, which represent something like 844 meters and something about 1,700 tons of equipment. It was also the opportunity to have a new portfolio of unique instruments, and also to make an innovative scientific instrumentation program. So I try to summarize by techniques to be more concise. So during phase 1, there was a lot of progress concerning the optics. We had a better focusing capability for elements like mirrors on plates, refractive lenses to reach this 10 picometer spot size limit. We also develop high heat load monochromators based on crystals and multilayers. On the engineering side, it was the opportunity to improve all the cooling system for crystals and multilayer monochromators, to continue on the development of multilayer based monochromator, and also to do a tremendous work on the stability to achieve a high stability. So the impact was, in fact, is to lower all the vibration and to minimize the thermal effect, thermal drift, by acting on the design and also on feedback systems. On electronic, the beamline needed specific detector development. We work a lot on all the motorized axes by developing many electronic cards. You can see the name of some cards, and the main one is the ESPP system that is used by other labs. And at Esrf, we have more than 5,000 or 6,000 of motorized axes. And also there was a huge development on on all the embedded processor, DSP, FPGA, CPU, etc. And it was the opportunity to modernize also the control system of the accelerator, which was based on TACO and the old technology, to move to Tango, which is a collaboration with 10 European partners, and which involve also industry, commercial company who help us for the development of software. And phase 2, which is the EBS phase 2, so we replaced all the storage rings. So it was a great opportunity also to redo all the engineering for the vacuum chambers, the magnets, girders, absorbers, and to develop also new materials to minimize the effect, to achieve a better vacuum in the storage ring, and also to improve the technology. What I can say concerning magnets, most of the dipoles of the storage ring were in the past in electromagnets, and the new one in UBS are based on permanent magnets, which in fact help to reduce the energy consumption of the new machine by nearly 20%. This phase also was the opportunity to continue the upgrade of the control system for the accelerators with all the graphics user interface, modern system, and also to replace the database which is used to store all the signals of the accelerators. We are storing more than 2,000 sensors equipment for the accelerator, and we needed to have a higher resolution possible database for the new accelerator. And there is also a lot of development. We have a machine simulator, so we can simulate a complete machine. It was very useful at the design phase, and it's still used with IA development to progress also on the maintenance and to predict any fault on the machine, and also to understand failures. There was also a lot of development on the electronic side. The main parts were the new timing system based on Rabbit technology, which was ready before the dismantling of the old machine, and also development of new power supplies, because now for the new machine, each magnet is powered individually. And we have what we call the hot swap manager. It means that when we have a failure on one single power supply, the power supply is automatically replaced by a spare one without losing the beam. So it's done in a very fast way. It's not fully operational at the moment, but because it takes time to do all the conditioning, I will say, and all the preparatory phase to implement it fully for the machine operation. So the upgrade program, in terms of technology, you see that we did a lot of improvement concerning the beam transport and conditioning with diffractive crystals and multi-layer technology. Now we have a new multi-layer machine that will be operational beginning 2022 with better characteristics and better capability. A lot of work on the refractive lens technology. Okay, we are producing in-house aluminum lenses, but we are dependent also on beryllium lenses and diamond lenses. There is still a huge development on diamond lenses, which are very promising and needed for the future. And also mirror technology. We are reaching nanometers, and so we rely on industry for producing such mirrors, but we need to have in-house also the capability to do the metrology of the mirrors, and for that we rely also on the industry and what industry can provide to us in terms of equipment. There was also, concerning end station integration, a lot of work to continue to do high precision mechanical system based when we reach nanometers. It's based on feedback loops, of course, and on ad hoc online metrology like interferometers, etc. Concerning the X-ray detectors, okay, we are using high performance X-ray detectors for commercial detectors, but we have started during phase 2 development phase for detectors with 2 families of detectors, high dynamic range diffraction detectors, and also noise-free high flux spatial resolution detectors. Concerning the control, we have also focused the renewal of the control system for the beamline. We call it BLISS. The old system was based on what we call the spec, and with this new system is mandatory to be able to have a higher acquisition rate for detectors and more online display capabilities also. What are our main projects now? So we are close to the end of phase 2. And as you can see, we still have a batch of new beamlines fully optimized for the new source to complete. We continue the refurbishment of beamlines, so it's an endless process, I would say. We implement all the data policy at Esrf, which is a huge program and a European collaboration. We are renewing the beamline control system, as I said, with also a huge part concerning the scientific software library, because there is the engineering phase, the engineering part, which is the control system, but also we have dedicated high-level scientific software, which are done commonly with scientists. We also have a program to further improve our insertion device and in vacuum undulator with small gaps, and also all the control related to do a gap scan linked to monochromators and beamline instrumentation, integration of commercial high-end 2D detectors that was done last year. And we also work on the remote operation, mailing, etc., all the access mode for the beamlines and scientific experiments. The scheduling, as I said, concerning EBS program, will be the financing will be completed in 2022, next year, and the program itself will end probably in 2023. In parallel, we have the regular refurbishment on beamlines. We have also the EBS beamline implementation. The four beamlines will be fully operational for the last one in 2025, 2026, probably. We are starting to launch development of what we call a scientific data management strategy, because with the new source and the new detectors, the amount of data that is produced every day, it's very huge, and we have to have all the technology ready to cope with all this data and data treatment. And for that, we need a new data center and all the associated software work that goes with it. And so it's a longer process that will probably start next year and for the next 10 years. We are still working on the optimization of the remote access and beamline automation, and also the improvement on the operation performance of the accelerator complex. There is still work to do on the lean act, on the booster, and for instance, to have we are using a topping up mode to fill the storage ring. And for the moment, there is the beamline sees some perturbation due to the injection process. So we have some improvement work to do. As I said, we are working on detector development technology, but this will be followed by an engineering phase for which we need industrial partners, of course. Main projects also. You see the picture of all the storage ring beam profile. You see the new one, and the improvement can be 2 order of magnitude, a factor of 100 for several beamlines, for some beamlines. So that means for us it's very challenging in terms of technology for what concerns the heat load, the stability, and the positioning, because the source is smaller now. Concerning the machine, we have some improvement, like addition of fourth generation cavity to improve the lifetime and the timing mode. There is an ID program for mini gap ondulators, but there is also a program to replace the klystron by a solid state amplifier. But in terms of technology also, we either for the coupler or for some ceramic chambers, kicker chambers, we are limited today by the possibility of ceramic manufacturing, ceramic process, I will say. So we need help from industry to be able to produce very difficult chambers, kicker chambers, and couplers. Is still ongoing development for everybody, I would say, all the sources. And concerning the digital ESRF, as I said, with the high flux now and of the source and the high flux of the detector, high throughput for the new detectors, we need to take care of all this data. And we have to work on the hardware and software side also for data reduction and data analysis tools. And if I go from the source to the data analysis, so for the source, we need a beam, stable beam and a good operation performance. And for that, the technology behind that is a lot of electronic and feedback system. For the optics, we need a stability, surface quality. And for that, what is important for us is the mirror polishing and also all the optical metrology, which is the key factor. Concerning the samples, we need to have a very precise positioning of the system, and we need to have systems that are able to move precisely, accurately, with high speed the samples. And for long range, it can be millimeters, but also maybe sometimes 10 centimeters. So for that, we need to have a very high precise mechanical system, and it's a mechatronic system, in fact. Concerning the detectors, we have concern about the pixel size, the signal noise ratio, and the acquisition speed. And so for that, the sensor technology and sensor material are very sensitive. We identify on the market some CMOS imaging camera that are very promising in terms of performance, but which need to be integrated to be fully used by the synchrotron community. And so for that, we can have also eventually have collaboration with other institutes or industry partners. And concerning data storage, for all the data, so we can produce terabytes of data every day by experiments. So for that, we need to renew our IT infrastructure, to put in place the data policy and all the associated software. Concerning data analysis, as I said, we need to have user-friendly software, because we have many partners who are coming to do experiments, but they are not able to treat data, because the amount of data is so huge and so complicated that we need to develop for them the necessary software to have a pre-treatment of the data. Concerning exploitation, renewal of beamlines, refurbishment, we have also all this common technology. I will not go through the list, but there is a lot of basic equipment that we renew every year, and for which we need industrial partners, of course. Concerning the detectors, just to summarize, we had these two types of detector technology under development. We are calling them Accelerator and Sphere. So it's the development. We hope to end this development by 2024. We are in process to have also we are collaborating with other partners in Europe, and we are open with other partners if possible. And for that, also for the engineering phase of this development, we will need help for industrial partners. We also develop for that high throughput technology, one called RASPA, which is the software part to take care of the high throughput data stream produced by the latest generation of detectors. And we have also LIMA2, which is a software framework to distribute the data to multi-computer backend. And we are using it for the young fraud detector at the moment. And this can be used for also for industrial commercial detectors to improve what exists at the moment. And as I said, for CMOS sensor camera that exists on the market, we have very promising families of camera that could be probably integrated for our use. So to summarize, as I said, for stability, we need a lot of electronic embedded software. So FPGA development is very important for us. For all the nano-positioning issue, we need also a lot of mechanics and electronic development. We identify also heat load issue. So microcooling is also an opportunity either for the engineering, but also for the detector part. And also 3D printing could be interesting either for microcooling or for other parts like vacuum chambers, for instance. And concerning detector technology, I said already, we need help from other institute and industrial partner to go to the engineering phase. And for all this instrumentation integration, we need we have the need of software development. We are doing a lot in-house, but we are open to outside companies to help us for development of software also. So I thank you for your attention.
Thank you, Jean-Claude, for such an interesting presentation about the upgrade phase 2 and future projects and technology challenges. Okay, the next speaker is Peter Spiele, the head of project division in charge of the FAIR and GSI synchrotrons. Peter, the floor is yours. Yes, I can see the full screen, but I don't have. Peter, please connect your microphone.
So now you can hear me?
Yes, it's okay.
Perfect. So
Yes.
now you should see the full screen, yeah?
Yes, it's okay.
Okay,
Thank you, Peter.
So thank you for the opportunity for in this round with all the or many large-scale projects, European projects. Great pleasure to introduce the FAIR project and the status. For those of you who are not so familiar with FAIR, this picture here gives you the outline. We have actually we are starting with a project with having in mind the construction of a larger number of facilities, but in the scope of execution, the project, it was, let's say, downscaled. We call that modularized start version. At present, we are realizing the modularized start versions 0 to 3. I will show you later on what the rest would have been, and which would be, of course, also an opportunity if at any time decided to increase or further upgrade FAIR, what that would mean for industry. FAIR is not only a project, FAIR is also a company according to German laws, GmbH. These are the shareholders. And the shareholders usually provide in-kind contribution to the project, but all the in-kind contributions are not made at only the institutes. They're also made with a strong involvement of industry. That's clear as usual. So FAIR is next to east to GSI. GSI is the Health Center in Germany, probably well known, exists since 40 years, with heavy ion accelerator facilities. And FAIR, actually, from the topology point of view, it's quite similar, consists of a primary beam facility which serves basically all ions. We accelerate from protons to uranium, more or less all ions, with different time structures, different intensities, high intensity, low intensity beams, generate secondary beams, rare isotope beams, and at FAIR also anti-proton beams, which can be injected into storage rings for further experiments. The modularized start version that we are presently realizing, 0 to 3, comprise a number of machines that we are presently building in parallel. A new proton LINAC, an extended high energy beam transport system, the superconducting heavy ion synchrotron SIS-100, a super fragment separator, antiproton production target collector ring, and high energy storage ring. This is what we are realizing at present. This is, of course, our focus at present. And the later versions, which we at present do not follow, but at least keeps the option open, for instance, for SIS-400, the tunnel size is made for later installation of a SIS-400 high energy fast ramp synchrotron on top of SIS-100 in the tunnel. So these options are still kept open, but no decision is taken yet to realize one of these machines. These are options for the after the completion of the modular start version. And there's many other options that we could have in mind, for instance, a high energy LINAC directly injecting heavy ions into cis-100, bypassing cis-18, or other opportunities. Of course, at present is the focus clearly here, realizing these modularized start version 0 to 3, and the goal is to have the first beam on target in 2025 and full completion of the modular start version in 2027. So this is the satellite view. Actually, this is a Google picture, not 100% updated, but at least it shows you the overall size of the construction area. We have separate the construction area in three sections: the northern part, and we call it the southern part, and the western part. And we are constructing here the blue and the green buildings with quite big progress. I can say that the civil construction is well under control, and the tunnel, cis-100 tunnel, is completed. We are now entering next year with the building infrastructure, and afterwards, end of next year, with the accelerator components. Also important is that the central supply building here is almost completed. The crossing building is complete. The link to cis-18 to the existing campus is completed, and we are constructing now the super FAS buildings, such that hopefully with completing these buildings also end of next year and entering with the machine and the technical infrastructure at latest in 2023. So that is well under control. It's a huge construction area, and progress is great, I must say. It's very impressive. Also on the accelerator side, we have a huge amount of components meanwhile produced. They are in storage areas nearby. There's about 3,000 big components stored meanwhile, and more deliveries are coming from various countries, shareholders from industry, and so on. As I said, aiming for start of installation and end of next year. So let's start with the existing machines, because fair means also that we have to upgrade the existing machines. We want higher intensities, we want higher rep rates, and so on. And as you know, we have a quite old machine. That's the universal linear accelerator. I think it's still the most powerful heavy ion LINAC in terms of, for instance, the most heavy elements, uranium intensity. We are usually talking about several milliamps of beam current, not about microamps, as others do for injection into this 18. This is our strength, is clearly heavy ion. And for that, we need also powerful heavy ion sources. And this very old LINAC is still working fine. We have, of course, in parallel to the project realization, a user program every year. And nevertheless, we are for fair upgrading this machine in order to provide also reliability for long duration operation over the next decades. For instance, we are going to replace the full second section of the machine, which is an Alvarez section, by a new Alvarez design, Alvarez type of LINAC. The first module has been built and delivered under testing. This alone is a quite big project which lasts over the next 10 years. There's many other topics: development of high intensity heavy ion sources, compact low energy beam transport system, advanced stripping technique, and RF matching topics here. We are also constructing for FAIR a new injector for proton ions, especially in order to generate high intensity proton beams for the anti-proton production. This LINAC the components are also under construction. The source is a development of the Saclay EFI source, provides 100 milliamps of pulsed proton beam. We have developed and almost, let's say, completed the manufacturing of a letter RFQ. And the second half is a CH warm room temperature section of CH cavities, where first cavities are also prototyped and in construction. The third LINAC topic that we have, this is more an R&D story, is the development and build-up of a CW heavy ion LINAC for a specific nuclear physics program that we have. They need high average intensities based on superconducting CH cavities, which are, let's say, in an advanced development phase, also having a room temperature front end. And behind that is all the knowledge and know-how that we have and developed with industry and institutional partners on H-mode cavities. As I said, we are replacing in the unit the second half by conventional alveolar structure, but we are also advancing the technology of H-mode cavities, which we have, for instance, in the high current injector, in the high charge state injector, which will be part of the new proton linac and the superconducting CH type cavity CW linac. This is the first tanks that we have built of these H-mode superconducting cavities, which will be installed in a tunnel parallel to the existing UNILAC tunnel, serving a specific, as I said, user program at GSI. We have also upgraded the existing CIS-18 with lots of conventional technologies, let's say at the limit of what is technically feasible. For instance, we have built a 240 or 50 kV injection septum. Main topic for the heavy ions is always vacuum, so we are aiming for extreme vacuum conditions in the machine. We have usually pulse fast ramp synchrotrons. So this machine, this is 18, is a machine which ramps with 10 Tesla per second with a pulse power of 50 megawatt. Every cycle can be different, perfectly under control with a precision of 10 to the minus 4, because we can change the ion species from cycle to cycle to run various user programs in parallel. So from cycle to cycle, we change all settings of the machine. The machine cycle is completely changed and the ion species as well. Though this needs the fast booster mode for CIS-100 injection has needed new cavities, new power converters, and new instrumentation on that program is basically done, completed. For CIS-100 and the later possible CIS-400, we have conducted especially the development of fast ramp superconducting magnets, not high field magnets, as for instance CERN does, but we are aiming for fast ramp magnets, and we have different technologies advanced for CIS-100 based on superferric magnets using a specific nucleotron cable. Low loss is always the topic, the key here. And for CIS-300, we have made a full-size prototype with our Italian colleagues, INFN, together, perfectly magnet, because it's a magnet which is ramped with 1 Tesla per second, which is very high for a Rutherford-based cable. This cable has been improved by various means in order to reduce the AC loss. And this magnet is just being tested again here in Germany to advance the limits of this technology. And we are further develop our knowledge here in terms of fast ramp superconducting magnets, for instance, by developing the HTS multi-layer HTS nucleotron cable, which may serve also future fast ramp synchrotron magnets. Another feature we are aiming for is full flexibility of superconducting machines, which means our machines are dominated by AC loss, which means every cycle generates a different heat load to the cryogenic system. And these huge range of heat loads and the big variation of heat load in the cryogenic system has to be kept under control, which needs specific developments for the local cryogenic systems and the cryogenic supply system. Though that is also quite unique, since many superconducting machines usually run the same or very similar cycles. We are running totally different cycles from cycle to cycle, low loss, high loss cycles, and this is a very demanding topic for the cryogenic system. Yeah, then of course, in general, collaboration with industry here a lot in terms of the CIS-100 superferric magnets, integration, design, manufacturing of components. All the CIS-100 superferric magnets for the dipole magnets are produced and tested, cold tested, and now we are in the integration of all quadrupole modules for CIS-100 with in-kind contribution from Russia. But a lot of these parts are, of course, made at industry, beam position monitors, cryogenic ion catchers, and other stories. As I said, in our case, heavy ions, since we are also running with low charge state heavy ions, where the cross sections for ionization is factor of 100 higher, vacuum is surviving. The beam lifetime is heavily affected by the large cross sections and any, let's say, any local pressure bump or locally enhanced pressure region. So CIS-100 is a cryogenic machine, is a superconducting machine, because we need a big cryo pump. This is not that we need the superconducting magnets, but we need a cryo pump. So that all the chambers are actively cooled with liquid helium. We have cryo adsorption pumps. We have cryo ion catchers, and also the room temperature sections are, let's say, at the limit of what you can do by neck coating and conventional pumping and conventional UHV systems. Lots of RF is needed. RF usually in the range of 0.5 megahertz to a few megahertz in our case. We are, I think, leading in the technology of inductively loaded cavities. We have just completed the manufacturing of 3 new magnetic alloy loaded cavities for fast ramping in SIS 18. We have completed the manufacturing of all ferrite loaded cavities for acceleration in SIS 100 and bunch compression in SIS 100. And all fair machines have usually ferrite loaded cavities using different magnetic alloy materials. Actually, we have surveyed all materials that are available on the world market. And for different purposes, feedback, acceleration, barrier bucket generation, debunching, and so on, we are producing such type of cavities together with industry. Different type of technologies you find in the, for instance, in the extraction straight of SIS 100, you have a lot of pulse power devices, extraction kicker systems, bipolar, ramped, then of course powerful megawatt scepter or radiation hard quadrupole magnets with magnesium oxide or cyan ester insulation, and high voltage devices up to 240 kV voltage. Another very specific machine is a super fragment separator. It's a machine which makes, where the front end is consisting of multiple separator stages, and the first section of this machine is basically a big beam dump where 99% of the beam is dumped in order to select the desired rare isotopes for the further experiments. And it's a machine which consists of a radiation hard first section and a superconducting part in the second section of the machine. And this is all large aperture magnets, of course, with a huge acceptance radiation hard magnets at the beginning, where we have prototyped, for instance, the dipoles with the Butker Institute. Superconducting magnets are contracted all to European industry and are tested at CERN in the big test facility. We have nice collaboration with CERN here in this area of testing large aperture superconducting magnets. And the multiplets, which are 66 tons devices, yeah, comprising quadrupoles, corrector magnets, and others, they are in production, and we are now approaching the serious production and testing with a huge helium content and so on. So iron-dominated superconducting magnets, huge weight, 66 tons each for the super fragment separator. FEA has also a large cryogenic facility, 18 kilowatt, as just seen in the CERN talk. This is the status of the central cryogenics building, which is completed next year. And we have contracted the cryogenic supply system, including the cold box, compressor, helium storage, and so on, to a company. And we have in-kind contributions. We are separating supply from local cryogenics of the machine, in-kind contributions, for instance, for SIS 100 and super fragment separator from different countries. For instance, we have serious production in transfer lines, which we call bypass lines, because they also contain busbar systems. The main magnet bus bars are going through these transfer lines, not only the helium, and so on. So this system is presently in the manufacturing. The components are in the manufacturing. Design is completed for the helium, for the cryogenic central facility, and the components are now produced such that we can start installation in a year from now. The storage rings comprise a little bit other technologies, also large apertures, heavy magnets as usual, and the magnetic alloy cavities, for instance, for debunching of the rare isotope beam or interproton beam, which is injected into the storage rings. But the main feature of the storage rings, since the secondary beams are also always of very poor quality, large size, big emittance, spread in longitudinal momentum spectrum, cooling is important. So we have a big expertise in beam cooling. And most of these cooling devices are in the design or development or already manufactured or in testing. A new invention by the Forschungszentrum Jülich is a slot ring coupler, which provides cooling in all planes at the same time. It's in the COSY storage ring installed for testing. And this is our, let's say, overview of beam cooling techniques that we have at GSI and at FEA in the collector ring, the HESR. But also in SIS 18, we have a cooler for injection optimization, and the cryo-ring. And we are developing new technology, a laser cooling technology for SIS 100. The HEP system is at most large aperture normal conducting magnets, a huge amount of power converters, which are provided as in-kind contribution of Indra, but also very demanding beam instrumentation system, for instance, the cryogenic current comparator, which can measure nanoamperes of beam current, or non-destructive diagnostics for the ionization beam profile monitor, which we have developed and just installed, for instance, SIS 18, and will also be used in SIS 100. This is, of course, not all technology we are interested in. I mean, in a 20 minutes talk, it's impossible to cover the full range, but some important topics is here. We are aiming for very intense heavy ion beams, and heavy ions, I talk about really the heaviest ions from the source in the range of 10 to 100 milliamps. Yeah, I mean, finally, you have to select according to charge state. At high repetition rates, for instance, at present, we are aiming for 3 Hertz. At very high currents, a big heat load to the source, which needs to be developed. We are usually probably world leading in H-mode normal conducting cavities for pulsed Linacs, and also superconducting H-mode cavities. Fast ramp superconducting magnets is a specific, let's say, feature that we have here developed for the FAIR machines. Low loss cable is the precondition for the fast ramp magnets. HGS nucleotron cable for the Cord Rutherford cable. High field superconducting Zepta we need for SIS 400, SIS 300, which we have also offered in terms of the conceptual design review for the FCC study. Magnetic alloy materials, magnetic alloy loaded cavities, a good quality factor for the RF system. Extreme UHV conditions far below 10 to the minus 11. There's a minus missing, sorry. Extreme pumping is needed, of course, neck coating, cryogenics, insert cryoadsorption pumps, and so on. Low desorption yield surfaces, because every impacting ion, you know that from photo desorption, we have ion-induced desorption, generates an ever-launching pressure increase local, and that is a big disaster for the heavy ions. So coating, surface structuring, and so on is interesting. Transition from power tubes, which are reliable and working smooth and fine, but maybe an issue in terms of supplier or types which where no commercial interest is anymore available. So from maybe high power switches, high power RF amplifiers to solid state technology, and new manufacturing technologies, 3D printing. We're just printing a CH type cavity. Additive manufacturing is called, and vacuum chambers, so that is certainly of interest for us. Thank you very much for listening. That's for the moment all.
Okay, Peter, thank you for your interesting presentation about the research and development project at the FAIR and the ASI. Okay, we have the 5, we are the 5 speaker is Thomas Thatcher, the scientific director at the European XFEL. We are grateful to you for taking part in this webinar. Thomas, can start your presentation.
Okay, yes, I think I did. So you probably see my slides.
Yes,
everybody?
Yes, it's okay. The sounds and okay, full screen. Okay, thank you.
Okay. Let's go. I tried to catch up some of the time. I'm a bit more brief than previous speakers. Just to introduce a few words on European XFEL, it's an international project. We have 12 shareholder countries. It's located in Hamburg, in the Hamburg area in northern Germany. It's an X-ray facility which uses a long superconducting accelerator to generate soft to hard X-rays for user experiments, in a sense very similar to what the Esrf is doing in Grenoble, but with very different pulse properties of the X-rays. We are collaborating very strongly here with DESY, who is running the accelerator for the project. That's why the facility starts also on the DESY campus here and is then having the experimental areas in Schenefeld, just west of Hamburg. I mean, these under the surface, so to say, I mean, this machine has, of course, a lot of technology. We run a 2 kilometer long superconducting accelerator. We have these very long undulator sections to generate the X-rays, and then we have a couple of very specific science instruments to really perform these scientific experiments. We control this from the DESI side for the accelerator area, and on the Schenefeld side for the scientific experiments. This is partly done by our people and partly done by user groups. And the really specifics of this facility is to provide extremely high quality X-ray pulses, which are very short, very intense. We provide high average fluxes and have coherent property radiations. And this is used for a range of very different scientific applications to solve societal challenge issues, in particular looking for new materials, for circular economy, and for biosystems to solve issues of new drugs and treatments. Of course, the second area is exploratory science, where we use basic science discoveries to pave the way for the next generation of technologies and develop in particular new methods to further our understanding of physical, chemical, and biochemical processes. So the theme overall is to really establish experiments which do the molecular, or which enable to take molecular movies. It's a synonym for many experiments we are doing. So you basically treat a certain system, you kick it with a laser pulse, and then you look at various times after this kick with an X-ray pulse to see the different state. And you see here on the right-hand side an animation of a rhodopsin molecule in our eyes, for example, where light is transferred into electrical signals. And that's exactly the structural changes that you see here. How the molecule moves is some of the things we want to investigate. So it can be also in very different systems, not only in biology, but also materials and so on. So what is the technology we use for that? So as I said already, we have this superconducting accelerator. So superconductor RF technology is one of our key technologies. We have here cryogenics, we use niobium. We also have, of course, many room temperature technology parts, high power RF diagnostics for the electron beam, many magnets. I mean, the total length of the accelerator is more than 3 kilometers. We have high power electron beam dumps. Then another key area is the FEL sources and beam transports. We use these very long undulators. We have in total several hundred meters of undulators. They are currently operated all in room temperature with permanent magnet technology. We need to measure these as well. So metrology is also a specialty we are doing here. We have extended vacuum systems, and we of course have a lot of X-ray optics and diagnostics to steer the X-ray beams to these scientific instruments. At the instruments, we operate a multitude of different X-ray techniques. We also have a very strong program for the last decade already on X-ray detectors, which we will extend in the future. I will come back to that. And we also developed optical lasers, which we need to do the pump of the systems we are studying. So these are megahertz lasers, which have femtosecond duration and very high timing accuracy. So this is also something which is very special and wasn't available on the market, and we had to develop ourselves in collaboration with commercial suppliers. And then something which becomes more and more important over the recent years is really, we have a fairly big footprint on data science. We not only generate lots of data, so we could actually generate, we have just had an experiment last week where we generated 7 petabytes of data over 7 days, so basically a petabyte per day. And you see you need also very high bandwidth and storage capacity to really enable such operation. We basically need also to analyze these data with the users. So data analysis as a service is a very important element, which is getting more and more important and will drive a lot of our requirements. And then last but not least, we also have a lot of construction issues behind and have these 6.4 kilometer of tunnels and underground halls. The facility is in operation since 2017. I mean, we started construction in 2009 and until 2016, and then basically took the facility into operation. So now we basically operate. We do typically 6 weeks per year interruption for maintenance and new installations, and do a continuous improvement of the installed hardware. That might be most relevant in this context. We will in spring 24 have a 6-month shutdown for maintenance of parts of the cryogenic accelerators. And we will at that moment also install a lot of additional instrumentation for the accelerator and the X-ray systems. But other than that, the machine is typically running, and only by around 2030, we expect to start a facility upgrade program, which will address the accelerator, the X-ray systems, and new tunnels and halls as we consider it today. But this still needs to be decided. That's our perspective for the future. In parallel to the operation, we of course do a lot of R&D in the moment to further develop the accelerator, the FEL sources and diagnostics, to further develop the X-ray beam transports and X-ray diagnostics, scientific applications and the data science. So this drives, so to say, concurrent activities and requirements to further know this. And so if you just look at the box down here, this is just the ongoing, so to say, replacement program for the accelerator, mostly, which is really replacement of electronics and computing hardware parts to their lifetime. We will install new hardware like the deflection expand deflecting structures for the accelerator, other devices to treat the electron beam. We do continuous development of the superconducting RF facility towards CW development, so that is development of cavities, injector, and so on. We will also construct there a test setup. And then we also, of course, continuously upgrade our data infrastructure, even for the accelerator, for example, to install 10 gigabyte and more powerful networks here. One example I just want to show here, because that's part of the backbone of the accelerator, is this micro TCA development, which has been started in Hamburg with many partners and is pursued now, and we use this quite significantly for the accelerator. And that's also, of course, when we upgrade the accelerator, there will be lots of new developments and replacements of these cards. So that's something which is ongoing and where we collaborate already strongly with industry, and we will continue to do this in the next decade. Let me say basically one slide about the European XFEL strategy 2030 plus. That's our long-term vision here in the moment. The major goals will be to provide the best research possibilities to support solving societal challenges of our time. So we want to stay an international leader in X-ray FEL methods and science applications. We want to broaden the research scope, and this of course drives some of the instrumentation we want to develop. So provide X-ray FEL radiation up into the very high photon energy range, so 30 to 70 keV for material science applications. Provide femtosecond and even shorter than femtosecond pulse durations to study functional materials, but also to simplify the access and the execution of experiments at European XFEL in order to overall broaden the ability for user groups to come to European XFEL. Furthermore, we have identified that we want to become a leader in data science relevant to these kind of facilities. So working with data, treating data, compressing data, this kind of stuff, which is really very relevant for us. And we think we will make an impact here in the European landscape, but also want to collaborate with partners here, of course. Major elements of this strategy, as we see it today, would be to optimize and extend the accelerator and the FEL sources to best cater for the scientific demand. So this would be to extend the accelerator portfolio. We currently operate in this burst mode acceleration, and we think about adding CW operation mode, so continuous delivery of pulses. That's a major extension to the accelerator. We want to also add some more intelligent operations, so distributing bunches depending on request, automatically changing properties, etc. We want to extend the FEL portfolio by different sources, and here in particular, the development of superconducting undulators is a strategic direction we just started a project on, and we consider this as one of the major development areas in the next decade. Similarly, we want to develop new devices for attosecond short pulses. And then to also cater for all the different instruments, we think that we need to optimize and construct new buildings. So we would probably modify the existing instruments, build new instruments, but also we think about building a second distribution building for the beam transports and FELs and an experiment hall. So that is a major extension of the facility that we're considering in the moment. Okay, and with that, I'm mostly done. So the acknowledgement goes to all the partners who have contributed to make this project a success and running. That's all I had today. Thanks for your attention.
Okay, Thomas, thank you very much for illustrating us on European future projects. And thank you again. Okay, the last speaker is Colin Carrier, the Uppsala University, explain the new and interesting future European project, the ESS Neutrino Superbeam project. I tried to share the presentation for Colin.
Thank you.
Yeah. I think it's okay, Colin. Yes.
It looks fine from here. Thank you, Manuel, for presenting my slides for me. I had a problem with my computer 10 days ago, which, as you can imagine, caused panic, but never mind. Here we are. So my presentation begins with a question, and that is, why are we here? Not why am I here in Sweden, or you are there in Madrid, or people are wherever they are, but rather, how is it that we on our planet exist? Because in the early days of the Big Bang, and we look back 13.6 billion years to that, processes occurred which should have annihilated all material in the universe. Matter and antimatter, which was created in the same quantities, should have annihilated and did not. And the question which is not understood is why it did not. What was the reason for this asymmetry, which meant that a very small amount of matter continued to exist and virtually no antimatter? And so the project that I am working on now with Uppsala is a neutrino factory for Europe. And it has the not very catchy name of ESS New for neutrino, SB for super beam. It will be the most intense beam of neutrinos in the world, and it will allow us to explore what are the differences between neutrinos and antineutrinos, and whether this will give us some indication of why matter dominated antimatter. So why are we here? So 13.6 billion years after the Big Bang, here I am in Lund, as shown in the bottom right, and we are on the same site as the European Spallation Source. We are a development project, and we're involved in design studies which are funded by the EU InfraDev program and previously by the COST initiative. So this is a new project which has not yet started to build. Next slide, please. So where is Lund? When I first came here in 2006, a lot of people that I spoke to in other parts of Europe didn't know where Lund was, and that's a great pity. So here on the left, I show where Lund is with respect to Sweden, right in the south. In top right, we see that Lund is connected to Copenhagen by a bridge. And this bridge is the famous bridge of the television program where all kinds of horrors occur, and which kept many people in, I think it's called Scandi Noir, but it certainly was very compelling. And that is the bridge. What it means is that between Copenhagen Airport and Lund, trains will take you 35 minutes to get to Lund. And once you're in Lund, bottom right, then there is a tram line which has been built to bring people directly up to Max 4 and ESS. And this is something which is ahead of time. CERN and the ILL Esrf in Grenoble took quite some time to get to that point. So Lund has got excellent connections. The city itself since we got the decision to build the European spallation source in Lund in 2009, the city population has increased by 1/3. Industry has been attracted. It's quite remarkable what has happened. Lund is really a university city, 45,000 students. As an Englishman coming to Sweden and now a Swede, I find it environmentally and socially very welcoming, industrially and academically first class. And one of the things that we pursued at the European Spallation Source was energy sustainability. And I thank Mats Lindros for his introduction. Next slide, please. So this is a photograph taken from the country road of the ESS site. Sitting in the front is Science Village. As you see, it's not yet developed, but there are significant plans for this as a support area. And a lot of industries are relocating here in order to take advantage of Max 4, where the new generation of focusing magnets were generated, now being installed at Esrf and elsewhere in the world. It was initiated here. Beyond, you see the ESS offices, and to the left, the tram line. So next slide, please. So ESS NUSB, what is it in a nutshell? It is basically a 5 megawatt upgrade in the accelerator of ESS so that it will be 10 megawatts. 5 megawatts itself is already the most powerful accelerator in the world. It's not there yet, as Matt said. But this will be extremely powerful, and therefore as a tool itself for other scientific disciplines than neutron scattering, material science, it is an excellent resource. And in this particular project, we talk about generating neutrinos, not neutrons. Neutrinos are everywhere, even as we're sitting here. Neutrinos are passing through us all the time. Roughly speaking, 6 times 10 to the 10 neutrinos per centimeter squared. In other words, I don't know whether you can see me or not, but in my thumb, 6 times 10 to the 10 neutrinos per second are passing through my thumb, your thumb. And yet we don't feel their existence because they are very penetrating and as a result, extremely difficult to detect. They were generated in the Big Bang, they're generated in the sun, they're generated in radioactive decay, they're generated in the Earth as well. And therefore, there is a lot of research on neutrinos from cosmological sources, but in this case, we are generating the neutrinos from an accelerator. To answer this question, why is there matter and no antimatter? Why do we exist? Why was there this asymmetry? The neutrinos that will be produced in Lund will be beamed through the surface of the Earth and detected roughly 500 kilometers away in an extremely large detector, 1 kilometer underground, which poses geological and engineering challenges. The capital cost will be around 1.5 billion euros. Excuse me. And we have 11 partners, including Spain. Next slide, please. So one thing about this project is that it is something which can be joined at the beginning. We are not a long running facility which is upgrading, but rather we are totally new. And this is then a photograph of the ESS from the air, thanks to Boris Tiltetov for this from ESS. Matt showed a slightly different slide, but that shaded white area to the left is the area which is dedicated for the neutrino facility. And the beam will pass from the left under the accelerator and to the right, and will pass just below that windmill that we see on the right. So next slide, please. And so this is the proposed area for ESS NUSB. This particular piece of land that you see, which is the ESS site, is of the order of 75 hectares, a large piece of land dedicated for the ESS. And we will therefore bring off the accelerator 5 megawatts of not protons, but H- ions, protons with 2 electrons, which will be brought into this compressor ring, which is barely visible. Blue and red are not good colors together. And the compressor ring will then take the 3 millisecond pulse from the ESS, and it will wind the long 3 millisecond pulse onto that compressor ring, and it will eject it in one turn. And we will then have an extremely intense 1 microsecond long pulse of protons, which will hit a target. Next slide, please. And the next one.
Yes, excuse me.
And the next one, yeah.
Yeah. Sorry, because they are stop.
Yeah, and that, right. And so
Right.
this one, the order of the slides is not ideal, but basically here on the right is the target. We see the compressor ring with the simulated protons at this point. There's a stripper foil, possibly laser stripping, as the H- beam comes into the compressor ring, and then it's flipped out on the opposite side to the target. This is extremely demanding technology. ESS itself, with 5 megawatts, is using a rotating tungsten target, and we will split the beam according to an earlier development of EuroNew into 4 individual targets: titanium spheres cooled by helium. Oh, excuse me. And the beam itself will be split into 4, and it will be directed 1, 2, 3, 4, and then 70 milliseconds later 1, 2, 3, 4, and we will then generate in that target pions, which are then focused into the forward direction. They decay into muons and muon neutrinos and are directed up to the north of Sweden. Next slide, please. And so here we see in a greatly compressed drawing, at the bottom we have the ESS accelerator, the compressor ring, the neutrino beam, and then the near detector, which is to monitor the beam and characterize it. It's a rather sophisticated detector. And then 500 kilometers away in the forest, in a place called Gartenbay, which most people have never heard of, we will install the very large detector. Next slide, please.
I have a problem with my.
And
sorry, excuse me.
don't worry.
Sorry, because the.
So you've got it there. Go back. That's it. So so here is a composite of various concepts. The neutrino detector, 500 kilometers from the European spallation source. It will be installed in a cavern 1 kilometer underground in the granite bedrock in Sweden, which is extremely stable because of the glaciation that occurred. The ground is very, very stable, and the rock is very, very strong. But to build a 100-meter cubed cavern is not a simple undertaking. The cavern will then be filled with 2 vessels, cylindrical, 100 meters by 65 meters. And as you say, a 100-meter cube cavern is not sufficiently big. And here, top right, we have Tord Ekdaler from Uppsala, who is the scientific project leader. And in the middle, we have the detector from Japan, Kamiokande, which is a factor of 10 times lower. And you see 3 brave Japanese in a boat going around and checking all of the photo multiplier tubes. And on the right, you see an underground photograph of the Garpenberg mine at the moment, but this is small compared to what will be necessary. Next slide, please. And so to the technical needs for this particular project, we will need a high power H- ion source. The current one has been built in Spain, and as we heard from Mats, is functioning well. We will need additional accelerating niobium cavities to take the beam up to 2.5 GeV. We will need to double the high voltage power supplies. When we go to the compressor ring, we will need a beam line of stainless steel, high quality, high vacuum tanks, focusing magnets, which will maintain the very intense proton beam in a finely focused ribbon. We will need high power target technology and of course radiation shielding. When we get to the detector, a single detector vessel, 100 meters tall, 65 meters in diameter. We will need all the control electronics, all the data processing methodology. We will need mining engineering beyond what has been done. CERN is extremely, extremely ambitious with their 100-meter FCC tunnel, but it is, if you like, linear. This is a 3-dimensional volume taken out even 1 kilometer below the ground. We will need water purification plants. This detector will contain 1 million tons of highly pure water. The detection of the neutrinos results in what is called Cherenkov light, and the Cherenkov light has got to be able to travel to the photomultiplier tubes. We will need thousands of photomultiplier tubes. Currently, these are built by Japanese companies. Why are there no Swedish, yes, and European companies that are competing here? We need that. We need design engineers, and we need many, many others in order to realize this particular project. So next slide, please.
Yes.
The one before that. That one. So those of you who are interested in getting involved, we would be delighted if you make contact. We are looking towards a second design phase. We're finishing a 4-year design phase now and the production of a conceptual design report. We will move on to another 4-year phase to get a technical design report. So that we are at a point where we are ready to build, let's say, pre-construction phase. We would be delighted if you want further details. You can find information on the website, which is there. We have produced 2 videos, one of them which is more conceptual, looking for an answer, why are we here? And the second one, more engineering design, and gives you a very good impression of what the facility would look like. And my email address is there. So if you would like to make contact, then I would welcome it. And I leave you with a slide, the final slide, please, of the partner nations. We have 11 partner countries. But as you see, many of them are missing. Germany, for example, is not there yet. We are still hopeful, and many other countries as well still to join. But as we begin to accelerate, sorry about that pun, but never mind, then we will attract more, and we will submit another bid to the infrastructure development program with a deadline of the end of March. So thank you for listening to me. And thank you also to Manuel and to Anna for helping to organize this morning's session. Thank you.
Thank you, Colin, talking through the different technologies that the ESS Neutrino Superbeam project is developing. Okay, now we move to the roundtable that will be moderated by my colleague Anna Hall, Director of Science, Sweden. And in this session, we will the opportunity to share the question asked in the question and answer session with the speakers. I ask the speaker and moderator activate your or connect your microphone and camera. Anna, please, the floor is yours.
Thank you so much, Manuel, and thank you so much to all speakers for these very nice presentations. And I really appreciate your effort to compromise and show all the new technologies that you need for the future, and also your challenges that you're addressing. And we have some open questions. Maybe we could start with those actually. And there's some for your Colin. Maybe we could start in that end. So Alan Zimmerman, for example, is asking, the ESS Superbeam sounds remarkably like June. If so, why both?
It is remarkably like June, but it's 10 times better. And June is now going ahead in the USA. And it will measure at what is called the first maximum of the neutrino oscillation. Our project, with its lower energy beam of neutrinos, will be able to operate at the second maximum. And the second maximum is much more sensitive to the effect that we're looking for. So whilst June is a first generation facility, we are a second generation facility. And a number of people, I know that there is a certain amount of this question, why June, or why 2, or why not hyper Kamiokande, and isn't that enough for you? Well, it's enough for us in the same way that FCC is being developed at CERN. Why is the LHC not enough? Because you have to go one step further. You have to build facilities not for your children, but in many cases for your children's children. And June will begin to operate far earlier than we will operate. In reality, I think if we detect a single neutrino before the end of 2030, it will have been quite an achievement. So the answer is that there is constant development of large research infrastructures, and you have to begin. And I would remind you that the ESS, the first meetings for the ESS were in 1988, and it will not be until what did Matt say? First beam on target.
24, I think.
Until 2024. So we're talking about 45 years from the first ideas for the ESS to the point at which there will be the first neutron, not a full program of neutron research. And therefore the answer to the question is, you have to think about the future and not just the present.
Thank you so much, Colin. So, I mean, 45 years is quite a long time that you need to be quite stubborn and determined. I'm impressed by all your scientists and all the people working around the research facilities.
They are really stubborn at the ESS, yes. I can tell you.
But that's in a positive way, I hope.
Oh, no, determined.
Determined, sounds good. Okay, there's one more question here around neutrinos. Why do you have to generate new neutrinos rather than capture the existing ones?
Because the existing ones are coming from all directions.
Okay.
And also the point of origin is not known in general, unless it's a supernova. The point of origin is not known. And the idea is that you start like that. You have a starting time, and you time the neutrinos as they travel to the detector, and you detect not the muon neutrinos, which were produced, but the electron neutrinos into which the muon neutrinos have evolved. And then you do the same for the antineutrinos, and you look at the difference. So it's basically time of flight over 500 kilometers.
Okay, thanks. Great, thank you so much. And then there is a question for Jean-Claude here around at ESRF. You're still with us, Jean-Claude, is that right?
Yes.
It's around does the ESRF also need beam shoppers required for the upgrades? So do you need beam shoppers for your upgrades?
We still have beam shoppers on several beam lines. I think recently one has been replaced on ID9 beam line. I don't expect a new need in the coming year, but probably this will be still required, and with a better performance. And I know that we can experience issue on stability, vibrations, because they are very sensitive to the environment, I would say. And also we need to progress probably for the reliability of these shoppers, because from time to time we experience failures, and so we still need support from companies to continue that work, I would say.
Thank you so much. And you also got an answer from Mats Lindros there. ESS also working with the shoppers, testing the one for the MEP right now. Thanks for that answer, Mats. And there was also a question here for CERN and for Jose Miguel. It is, so now you have been working with the High Lumi project for quite a number of years. In what way can you use experience in working with the industry in High Lumi for future projects around FCC and CLIC?
Well, let's start with high luminosity, and then I will come back to CLIC. So high luminosity, we've been developing new technologies for the high field magnets, so pushing the niobium 13 towards let's say the first step in its limits. And this was done on a kind of prototyping and pre-series level. And obviously, if we want to build these magnets in large quantities, the industrial approach has to be completely reviewed, in particular all the risk management and tolerances of these mechanical assemblies. So certainly there we will have to go through a very large iteration in order to bring that technology to a maturity level which will be compatible with a large scale that we are talking about. Okay. And so this is the key for the high luminosity. For the CLIC, the situation is slightly different because these modules, the RF modules have been produced already by industry, and the tolerances and the manufacturing capacities of the industry are matching exactly what is required. So as it was shown by Steiner in the slide that I was presenting, Steiner Stapnes, I mean, CLIC is already at a very high maturity level. So I think that we will be in capacity to go directly with industry without major issues.
Has industry been involved in the development of CLIC? Have you yes. Industrial contacts to?
Yes. Yeah. I mean, most. I mean, the X-band klystron have been produced in industry, and most of the modules have been machined in different companies across Europe. So yes, indeed, this has been done closely with industry. Yes.
Thank you so much. And there has been a number of questions also that actually there is answers in writings in the Q&A modules. I have one question for you also. What strikes me when I listen to your presentations is that actually you have a lot of similar technology challenges. It's about high energy, high power, cryogenics, vacuum, superconductivity magnets, new detectors. That's Mats Lindros and one of you and many of you lifted up, instruments, new material, 3D printing that Peter at FAIR lifted up, for example, data acquisition, AI, and both on the control system and the experiment side. You talked, many of you, about software development and XFEL, quite impressive. You talked about data science and how you have gathered 7 petabytes over 7 days. Very impressive, XFEL. So one question I have to all of you, maybe we can do a round table really quick. If you need to, what area do you think is the most important to co-develop with industry? I mean, a lot of things is happening within the industry right now. So what area do you think that the facilities really, really need to co-develop with industry? Maybe we can start with you, Mats Linderos. What do you think is the most important area in the new technologies for the research facilities to co-develop with industry? What do you say, Mats?
Did you refer specifically to software development?
No, I refer to, you have a lot of technology challenges as you lifted up and sum up in your slides. And if you just can pick one of these areas, where do you need to co-develop with industry really to make a difference and really solve challenges?
It's a big question, of course, but because, as you said, I mean, technology development in industry is in core of what we are doing, and often it is the labs that then drive prototyping and experimenting, and then eventually, once it's mature enough, we turn to industry to order prototypes and see how manufacturing can be made efficient, and prices then come down to something reasonable that we can afford for our facilities. But I think over the coming years at ESS, it's probably going to be on the detector side where the biggest needs are. And there are, because of global shortage of helium-3, or at least the fact that the strategic reserves are kept quite tight by the big countries, the alternative technologies, which, for example, in Linköping of the borated detectors, and similarly at CA, for example, we're doing our neutron beam loss monitors using micromega technology, and then doing neutron conversion, both fast and slow. But all these things, will improve the detector's efficiency and capability, and I think that's the most immediate need. And to make these big detector arrays, because, for example, the borated neutron detectors, they are demonstrated. Some of them are under manufacturing, but some of them still needs development, and that's typically the industry development that adds to making this possible.
So detector development. And Thomas, XFEL, what would you pick if you could pick one area to co-develop with industry? Which one would be the most important?
It depends, of course, a little bit on the phase, correct? I mean, during construction, I would have immediately said, the development of the accelerator technologies, in particular for the niobium cavity production, was the most important element we did together with industry. But now we're in the operation phase, and so things have changed. And I would maybe join Mats in saying that for us, probably a critical area is detectors. We are just about to start a new detector development program for the next decade. See a real problem there, because we do this mostly through scientific collaborations with other scientific partners and universities and other installations. And industry is mostly coming in at a very late step, correct? Just in production. So that, and we see very much shortage there. If you just talk about silicon technology, it's getting very difficult for us to get access to silicon manufacturing, and that becomes a real bottleneck. And so we are, of course, at the very small demand here compared to big chip industries. But that's for us a real challenge, and I think that will limit us in the next decade. So their joint collaborations would be really highly beneficial. Though I think we understand that we are not a real market for chip supplies and chip development. So that's a challenge. One has to go to small and medium enterprises who are specialized on such kind of chip production. I would, for us, would be the biggest benefit for the next decade if you could engage in common developments here.
Interesting, super interesting. And Jose Miguel, at CERN, what do you think would be the most important area to co-develop with industry?
Even though I'm leading the technologies, I'm going to be less ambitious than my colleague. I think the infrastructure services is clearly the area where we have to optimize. with industry. I mean, first, because the industry is much more advanced than us. I mean, we have experts running the system, but we don't have experts to design the system. So we have to optimize the cooling and ventilation. We have to optimize the cryogenic system, the quantity of liquid helium, the quantity of liquid argon. We have to optimize the energy consumptions. I mean, today, just to give a figure, I mean, the increase of the electricity is having an impact between 30 and 40 million on a yearly operation budget of LHC. So in 10 years, this is 300 million, which is quite some money. So I think we cannot continue thinking that we should not go through the phase of optimization of all these industrial services. And I would like to put as well inside the controls, because of the legacy and obsolescence. I mean, we have big problem with that. I mean, changing the control system of all CERN accelerators is close to 100 million. And again, I mean, we are designing machine for 20, 30 years, and these control systems are not surviving more than 10 years. And this is a problem.
So optimization. And if you're industry that you feel that you could really contribute, how could you proceed then? You connect with your colleagues at CERN, or how do you proceed if you feel you have this competence as an industry?
But I think for me, the first thing is that we really have to create the forums to discuss with some companies who are already involved in these kinds of initiatives through mutual collaboration or through European network, and see and get convinced that we need to go through that step, and we don't have to do it inside. So going through the limits of the what I call the syndrome of not invented here, sometimes things are invented outside are also quite interesting, and we have to be open-minded and look at it.
Great, thank you so much. Thanks. And Jean-Claude, Esrf, you did a very nice presentation. I think you were very precise. All of you did good presentations, but you have really listed your need. If you could pick one need, Jean-Claude, that is he still here?
Yes. So if you can pick one, I will say that I will support fully what just Thomas said. The detector part for us is very important, very challenging, and we cannot compete with industry when you have industry or labs putting several, something like 40, 50 million to develop a chip. A lab like Esrf cannot compete with that, and so for that we need collaboration with other institutes to have some common view and to have more power face to the industry, to have access to some material like the CZT material for high energy sensors, for which today we have difficulty to have access. So this part is very important also for the engineering phase of the detectors. And what is important also is all this data produced by detectors. We can also imagine to have a embedded software in the detector itself, to have a pre-treatment, to take only the useful data from the detector before the data are produced. And after, our main challenge also is, once the data are produced, is to make them available for the community, so that if once an experiment is done, maybe in 5 or 10 years' time, one scientist will find something useful in the experiment, and not to have to redo the experiment every year or many times. And that will save money, brain, and energy, I think.
Yes. So actually, both hardware side, the computer chip, and how you get, I mean, physically get the detector to work, and but also the once the data is produced, how to handle the data. Maybe use AI to sort out what data to collect and save, and what not to collect, and also in that, maybe it also can become with data centers and so forth, how to do that in an energy efficient way. Green computing and so forth, I assume, is a big challenge for you. Yeah, okay. So detectors, very, very important. Great, thanks. And FAIR, Peter, what do you say? If there's one area that you would like to collaborate and co-develop with industry, what would you pick?
And I know that you want a simple answer, but I think it's very difficult to give a simple answer because every machine has specific technologies and every machine, and actually among us, there's very, very different machines, electron accelerators, heavy ion accelerators, and others. I know that the technologies are quite different, and also you hear always the same keywords. They sound very similar, but if you look into the details, things are still different. I personally believe that the first approach is that industry has to maintain their knowledge and experience and skilled people in engineering. It is impossible to build such big projects and machines only with the experience of the resources and people at the institutes. We need industry and we need experienced engineers in industry to cooperate with us. Otherwise, such big facilities cannot be built. So maintain knowledge is extremely important. Then the other topic is for sure, the pressure among us will increase in terms of technology transfer. Because there's lots of topics in our society which need to be addressed, and we are probably getting significantly more under power to look at the commercial or social applications of the things we do. So technology is important. That means better collaboration in terms of let's say dual use of technologies we are developing for the accelerators in terms of applications and commercializations. I come back to the point from Miguel. The precondition of running our machines is energy, stable power grids. We will get in severe trouble if we continue with energy policy as we do with running our machines, not only the electricity bill, which we also have to pay now much higher prices, also the stability of the power grid for we are all large consumers, is important, and the interaction with the power grid. We are still used to run in systems which are extremely stable. I hope it is maintained, and this is more an industrial and social aspect. And then one topic I think is, as I said, looking into the use of the technologies we develop in terms of these big topics in society. Is we develop something together with industry and look where it can be applied to the big questions. So I give you an example. We are developing a new HTS multi-layer superconducting cable. Of course, precondition is that we can produce long tapes of HTS material cheap, if possible, and very thin, narrow tapes carrying high currents, of course. And then we can build such a cable, and then we can look for applications, for instance, in energy transmission, in energy storage, in other topics we have in society, also in, of course, fusion energy. And that means, we have enhanced, let's say, our looking left and right into the things we do with respect to what is a potential application for the big questions in our societies. HTS, higher coolant temperatures, helium gas cooling is energy efficient. Energy efficiency is a very important keyword, I think.
Great, thanks. Thank you so much for that. Thanks. Colin, a last remark. If you could pick one area that you would like to co-develop with industry, what would you pick?
Well, it has to be, for me, energy sustainability. Jose Miguel has already mentioned this. We will price ourselves out of the market unless we have a very credible energy policy. ESS in 2009 developed an energy neutral strategy whereby we would have owned our means of production, 20 windmills. This frightened to death our partner countries. They wouldn't think about it. However, if it had happened, it would have meant that we had control of when we operated and our budget. And so I think that energy sustainability nowadays has come of age, and all big facilities have got to look at that. And these ideas come from all kinds of places. The ideas from ESS came from, for example, the showrooms of Toyota, who wanted to be energy neutral for their car production. and they targeted showrooms. Airports are being developed to be energy neutral. Why not science facilities? Existing facilities is very difficult to backfit for energy sustainability. But if it's not done, FCC, for example, ESS will take 30 megawatts. What will FCC take? 100 megawatts? You can't pay for that. So that's one thing. The second thing, politics and decision making. Industry and scientists have got to be forever talking to the decision makers. Politics can delay a project beyond the lifetime of a human being, and that's not acceptable. If you look at since the Second World War, it's just taken longer and longer and longer to produce facilities. And the third thing, going back to what Mats Lindros said, and that is you must protect your essential strategic supplies. The helium-3 question, which I lived through, was a political thing more than people said supplies, but it was political. Helium-3 and tritium are intricately related, and tritium is used for certain devices that go bang in the night. And therefore, you have to protect your strategic supplies. And the EU have got to get together on this kind of thing, in my view.
Thank you so much. So I mean, if I just summarize all of you, it's about both how you interact with the society and, of course, energy, stable power grids, and also in a bigger picture, but also how you can, as a facility, be energy neutral if you're being built, or how you can optimize your energy consumption and really work with that question in a hands-on way. There you could also work with industry, because a lot of industry go through that. Very, very interesting. And also, I mean, if I listen to all of you here, you also lift this societal, how you can interact with the society in a more efficient way, both getting skilled people, engineers depend on how we can foster competence in Europe, but also how we can work with the dual use. You develop a lot of interesting technologies. How can we use them to get answers for the big questions and our society challenges? And then you also lifted up, many of you, the detectors, and of course the detectors are hardware, which also are challenges with industry, but also the software and how we work with the data mining, AI for sorting out data. And data is something that we produce more and more in society, and this is an area where I really think that industry and the research facility can work together for the future. So thank you so much for all of you contributing to this question and answer session. And I now leave the word back to Manuel.
Yes,
thank you.
Thank you to all the speakers and to Anna for being moderating this interesting roundtable. And well, okay, the presentation will be able on the webinar web page. And okay, many interesting topics we are presenting in this webinar. We hope it has sparked your interest to explore further opportunities in the second edition of the B-Science Business Forum in Granada between the 4th and 7th October 2022. Please check the information on the BSBF website. So again, thank you everyone for attending this webinar, and goodbye.
Thank you.
Thank you.
Bye.
Bye.
Thank you.
Thanks a lot.
Bye.
Bye. Bye.
Thank you. Goodbye.
Bye.
Bye-bye.
Bye, Matt.